Hello, my name is Aditya Pillai and this is my second lab report. The purpose of this lab is to use the previously calculated charge magnitude to model distributed electric force/electric field. The models and fundamental physical principles used are the principle of gravity, F equals mg, and electric force/Coulomb's law, F equals 1 over 4 pi epsilon naught times q1 q2 over r squared. The report shows the charge is positively charged with a magnitude of 7 times e to the negative 9 coulombs, and that the distributed charge shows lower electric force as the number of points are increased. Some of the assumptions we made are that there was no drag force, that the tapes are treated as point charges to calculate the charge, but as distributed charges when calculating the electric force again in the coded model, that the U-tapes had about the same amount of charge as they were made by the same methods, that the pen used to test charge sign was negatively charged as specified by the lab instructions, that the mass of tape is about 1 gram per meter of the roll, is a sphere of diameter 1 e to the negative 10 meters, that an electron has a charge negative 1.6 e negative 19 coulombs, that tape has a height of 25.4 microns, or 0.0000254 meters, and that the tape we used was exactly 20 centimeters long and 2 centimeters wide at all points. In this lab, the system is the tapes, and the surrounding is everything else. For this lab, the initial conditions had the tapes charged at the same magnitude, and the top tip held just so that it floats above the bottom tape. Some of the observations made are that when the two tapes were brought together, they repelled each other, confirming same charge, but when brought to a neutral object, they were attracted due to the induced dipole. When the charged tape, assumed to be negatively charged, was brought near a neutral object, it was attracted, and when brought to the tape was also attracted, meaning the tape is likely positively charged. The tape is not in motion when floating, meaning that the tape is likely experiencing a net force of 0. Since gravity and electric force are the only ones acting on the y direction, the magnitude of gravity can be assumed to be the magnitude of electric force as well. Since the density of the tape we use is 1 gram per meter of the roll, the mass is 1 gram per meter times 0.2 meters, which is equal to 0.2 grams. The gravitational force on the tape, therefore, is m times g equals 0.2 grams times 1 kilogram over 1,000 grams times 9.8 meters per second squared, which is 0.00196 newtons downwards. The magnitude of the electric force is the magnitude of the gravitational force, since we assume they're equal, which is also equal to 0.00196 newtons upward in this case. The displacement between the two tapes at rest is 1.5 centimeters, or 0.015 meters. F electric equals 0.00196 is equal to 1 over 4 pi epsilon naught times q1 q2 over r squared. Since q1 and q2 are assumed to be equal, and the displacement is 0.015 meters, q1 squared is equal to F electric times 1 over 4 pi epsilon naught to the negative 1 times r squared, which gives us a charge of 7e negative 9, positively charged, which is deduced from the Penn experiment. For this lab, unlike the previous one, there are two for loops that add up the effects of each individual sphere that we use to calculate the charge in the bottom tape, and its effects on the individual spheres that represent each individual charge in the top tape to quantify the total electric field effect and as well as the total electric force effect of the bottom tape on the top tape. Since we are able to change the amount of spheres representing the top and bottom tapes, we can also see how this affects the electric force calculated. And as shown, as you increase the number of spheres, the magnitude of the electric force decreases. The top left example shows 2 spheres, with the magnitude of the electric force being half of what we would expect it to be. The top right picture shows it with 10 spheres, which shows the magnitude of electric force at 2.72 e to the negative 4. And finally, in the bottom left, we see the magnitude of the electric force being 2.61 e negative 4 at 20 spheres, showing this decrease. If you wish to access the code yourself, you may follow this link or scan this QR code to access the code that I've made. To finish this lab, we were asked to answer 2 questions. The first is, what if you had modeled each of your tapes as a single point charge like the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you get with your line charge model. With a point charge model, we got a calculated electric force value of 0.00196 newtons. With a line charge model, we got a value of 0.000273 newtons, assuming 10 nodes, a value about 17% as big as the experimental value we calculated with the point charge model. Another question we were asked is, why do these estimates differ? Which value is more likely to be closer to the real value, and why? And the answer is, these estimates differ because the distribution of charge means a greater distance between different points on the tape. Thus, the distributed charge model of this lab is likely more accurate since it takes into account the variable distance between different charged points on the tape, and therefore the different electric force effects from each individual charged point from the bottom tape on the top tape. Thank you for listening to this presentation.